It is always a great privilege and great joy to interact with China and with Chinese scientists in the largest planet Earth. ICRANet has been very much linked to China, and before even the establishment of ICRANet, we took with Professor Cho Pei-Wan the decision of bringing the third Marcel Grossman meeting in China. Don't distract something, because this is important. And at that moment, that time, we had in the committee, we still have Steven Weinberg in the committee, International Organizing Committee of the Marcel Grossman meeting. But we had also another distinguished scientist from Israel, Yuval Neyman, in the International Organizing Committee. And when we decided to go, and of course Yuval was an hero because he was related to Salam, because Salam had been his teacher in physics at Imperial College. Therefore, in this family, we decided to have the meeting in Shanghai. And difficulty came because the sentence was, friends from all over the world are welcome, all over China. But at the moment of coming to the point, the decision was that we will not allow to have Israeli to MG3. Well, you can read the fantastic story of the negotiation. It was solved in the Chinese imperial way. After 7 days of discussion in which I had the folly to go to Beijing alone, and discussion over and over, at the end of the week the solution was found, and 2 Israeli, not one, could come. One of them, Tzvi Piran, who is still here at this Grossman meeting. Was a great joy for everyone. The meeting, the third Grossman meeting at Shanghai was one of the first great success. And my attachment to China has always been very strong, so strong that in this MG14, we decided to make a detour before coming to Rome to have the Marcel Grossman Award to be delivered to T.D. Lee and Xian Yang. And you can all read the splendid answer of Xian Yang to the recalling Fermi. And therefore, tonight, to have something with us is a continuation of this long joy of the relation with China, but not only with China, because Sam has been operating all over the planet, and when he has covered all over the planet, has moved even over the planet doing fundamental physics from the space station. To this adventure is testified by the presence of the president of the Italian Space Agency here with us, Roberto Battistone, who has been the chairman this morning. I have the enormous pleasure to ask Professor Ting to come to deliver his talk.
Mr. Chairman, should I give my talk in Chinese? I'm very pleased to be here. When I was a student at the University of Michigan, I had good grades, and so like all the students with good grades, I thought I should do theoretical physics. So I worked with George Uhlenbeck. This morning there was an Uhlenbeck professor. After about 1 month, Uhlenbeck invited all his graduate students to have a tea with him. And he told all his graduate students that if he were to do his life over again, he would rather be an experimental physicist than a theoretical physicist. I was very surprised. Here's one of the great physicists of the 20th century. So I asked him why. He said, an average experimentalist is very useful, an average theorist is not. That little 5-minute conversation convinced me I was in the wrong place. So I told him, I'm leaving. And so that's how I became an experimentalist. When I started, I really didn't know anything. Because at the University of Michigan, they have, it's a very good school, and you can go to this school, you can work very hard, and you can just pass by. And I decided to go to the football instead of taking classes. And so I was there 6 years, from freshman to PhD. It's considered very fast. Normally it takes about 10 years. In these 6 years, I learned everything about University of Michigan football and learned very little about physics. I started learning physics when I come to CERN and working with an Italian physicist, Giuseppe Cocconi. It's from him I began to learn physics. So what I would like to do today is to share with you my personal encounters with physics. I may need a pointer. So, to start with, let me mention, today the problems which challenge us are immense. How can these challenges be met with tools we have developed? I would like to read a short passage. Humanity is being ravaged by disease. Doctors are powerless against it. Pollution is everywhere. Men and women die daily in senseless ethnic conflict. Homelessness is rampant. People can't read. Children are being killed in the street. And this was Europe in the year 1350. Yet from this period of despair, destruction, and disillusionment sprung the greatest period of hope, new ideas and creative expression. The Renaissance was born in Italy and spread throughout Europe, transforming how people look at the world and their place in it. Scientists re-examined old ideas about the nature of the universe inherited from ancient Greeks and Romans. Modern science, or the understanding of nature phenomena using experimental techniques, was established during that time. So the development of accelerator has long history. The earliest accelerator still exists today, at very low energy, but perhaps have done the most important work. This is the largest accelerator, has a circumference of 27 kilometers, and goes to very, very high energy. And we say you will study the fundamental building blocks of nature. So after so many years, we now know outside the atom is the electron. Inside its nucleus, inside the nucleus are particles, inside the particle are quarks. So let me share with you 5 short stories. The first story is measuring the size of the electron. Modern electromagnetic theory proposed by Feynman, Schwinger, and Tomonaga in 1948 required the electron has no measurable size. The theory agreed well with all experiments until a large electron accelerator built jointly by Harvard and the MIT provided the most sensitive measurement of the size of the electron. This experiment was done by world's leading expert in the field, who has spent many, many years developing the technology for this experiment. So this is the result. The measurement compared with theory of Feynman, Schwinger, Tomonaga, based on electron has 0 dimension. Theory equal to 1 means experiment agree with theory. This measurement shows a clear deviation from quantum electrodynamics. What is measured is the distance to the center of the electron. So this shows the electron has a radius of 10 to the minus 13 to 10 to the minus 14 centimeters. Most importantly, this experiment was independently confirmed by a respected group at Cornell Electron Accelerator. The Cambridge Electron Accelerator is the first large electron accelerator, has a circumference about 300 meters, so the electron goes through the accelerator, emits light rays of energy of 6 billion electron volts. And with this high energy light rays, you can probe inside the electrons and look at its radius. Since those results touch upon the foundations of modern physics, I decided to repeat the experiment with an independent method. At that time, I just got my degree from Michigan. I never have done any experiment by myself and knew nothing about electron physics. So I received no support in the United States. And so in 1965, I decided to leave Columbia University and move to the newly built 6 billion electron volt accelerator DESY in Hamburg to redo this experiment. When you are young, you don't really care about who supports you. So this was the first experiment I did with intensive photon produce electron positron pairs. There's a magnet, Cherenkov counters, magnet, and Cherenkov counters, and shown in here. And this is Professor Stu Smith, and now I think he's vice president, former young collaborator with me. Now I think it's vice president for research at Princeton. So after 10 months, in 1966, we repeat the experiment with a different method and discovered that all measurement compare theory is in perfect agreement. And the electron has no measurable size. And the size is less than 10 to the minus 14 centimeter. So My first lesson is probably it's a good idea not always accept the opinion of the experts. Because before our experiment in Hamburg, and there were Harvard group, MIT group, and Cornell group have done experiment and getting the different results. The second story I will share with you is the discovery of new family of quarks. By 1970, all the known elementary particles could be traced to three kinds of quarks. A pi would be like this, a proton would be like this. So I asked, why only three kinds of quarks? To look for new quark, I decided to set up a very sensitive detector with a sensitivity for new quark compared to old quark with a sensitivity 1 part in 10 to the 10. 1 part in 10 to the 10 means during the rainstorm over Rome, there are about 10 billion raindrops per second. And you try to find one drop that has a slightly different color. So this experiment was not popular with the physics community because the theorists believe that there are only three kinds of quarks. Why that? It's because you can explain all the known phenomena. The experimentalists think no one can believe such a difficult experiment can be carried out. And so the experiment was rejected nearly by all the accelerator laboratories. Finally, in Brookhaven National Laboratory, they accept this experiment. So we set up a spectrometer with a beam coming in 10 to the 10 particles per second. The equivalent luminosity is about 10 to the 36. On a target, have a magnetic spectrometer with very precise detectors. And so the measured background to signal separations larger than 10 to the 10, and the mass resolution is 5 parts in 10 to the 4. And to our great surprise, suddenly at 3.1 GeV, there's a very sharp peak. And the width of the peak gives its lifetime. The lifetime is 10,000 times longer than all the known mesons. The significance of this discovery is similar to suddenly you discover in a remote region on Earth a village where people instead of live to 100 years, but live to about 1 billion years. So that means these people are somewhat different. Indeed, when you look at what we call a J particle, after this, many particles were discovered. They transact by emitting absorption photons to each other, very much like the triplets of positronium, meaning it's a combination of two new quarks. So this implies the existence of a new form of matter made of new kind of quark. So the concept of three kind of quark was wrong, and we now know that there are at least 6 kind of quarks. We call them U, D, S, C, B, and T. So my second lesson is keep faith to yourself, do what you think is right, and listen to the presentation at CERN about Hess and CTA. Give me the same impression. It's very important to keep faith to yourself. I was very impressed by those presentations. My third story is the observation of gluons. Gluon is the carrier of forces between quarks. In nature, we have gravitation, discovered in 1612. Still today, there are many theories, but we have yet a concrete, repetitive result to find what is the carrier. The electroweak is carried by gamma ray, Z, and W. Nuclear force is carried by gluons. In the late 70s, the world's first large electron-positron collider has an energy 46 billion electron volt, a circumference of 7 kilometers, and in 4 places, the electron-positron collide. And this is our detector. The original purpose of the experiment was to continue to measure the radius of the electron, and just to find why the electron doesn't have a measurable size. Accidentally, we found when you have a positron-electron collide, you can produce quark, anti-quark, and you may produce a gluon. With the increase in energy of gluon, instead of the 2 jets from quark, anti-quark, and you can see 3 quarks. Now, many reactions produce 3 quarks, but the major 3 quarks, when you put them out on a plane, agreed with quantum chromodynamics. And this was shown in the Physics Today of February 1980. So this was a total surprise, because we certainly didn't think of it. Nobody thought about it, but it was accidentally discovered. My 4th story, I only have 5 stories. My 4th story is large international scientific collaboration. It's on experiment called L3 at a 27-kilometer electron-positron collider. This experiment lasted more than 20 years, involving 20 countries. Why it's 20 countries? Originally was about 15, and during this experiment, the former Soviet Union suddenly become many more countries. That's why we have 20 countries. And this experiment received strong support from INF in Italy. So I have had a long history of very successful collaboration with the Italian physicists, from the intersection storage ring. That's when I first met the president of the Italian Space Agency, and in L3, and there's Roberto and Bruna, Giovanni, Ambrosi, and in AMS also. So these people has a very long history of collaboration. So what is the basic idea of this experiment? When you have 100 billion electron volt electron, 100 billion electron volt positron collide, during the collision, you produce very high temperature. The temperature is 400 billion times the surface of the sun. If the universe comes from a big explosion, what you're doing is in the laboratory, in a controlled, repetitive way, to create the first beginning of the universe. I already mentioned we now experimentally prove the world is made out of point-like particles. 6 quarks, 3 types of electrons, and their associated neutrinos. With this, you can ask a simple question. How many types of electrons are there? Why there are only 3? How large are the electrons? An old interest of mine, try to see whether you can see a measurable size. Can electron be divided into smaller particles? Mr. Chairman, you must remember I'm an experimentalist. So you ask this kind of experimental question. Then you ask, how many quarks are there? At the beginning, everybody believed there were 3, and we discovered the 4th, 5th, and 6th. The question is, does it end there? How large are the quarks? Can quarks be divided into smaller particles? So this is the detector. It's about a little bit smaller than the size of this hole. There's a very precise vertex detector surrounded by crystals, surrounded by 300 tons of uranium, and surrounded by a large muon detector and by a magnet, and this is the coil of the magnet. And this is a return ion. And so electron goes through the detector, will leave this type of trace, muon this type of trace, photon like this, nuclear particle will look like this. Key to this experiment is a very precise silicon detector, very, very close to the beam. And this is the first use of double-sided silicon vertex detector with a resolution of 8.6 micron, proposed and carried out by Roberto Battistone and company in Italy. So this is the L3 experiment. After 20 years, 300 papers were published, 300 PhD theses, but basically all the 300 papers can be summarized in few sentences. By the way, this is the front page of Scientific American, depict computer reconstruction of one of the events. The result shows there are only 3 kinds of electrons within the mass region we can reach. There are 6 kinds of quarks within the mass region we can reach. Electrons and quarks has no size. Their radius is less than 10 to the minus 17 centimeter. The 300 papers, the results are in excellent agreement with the standard model and set the Higgs mass limit of 112 GeV. The result in good agreement with standard model is most unfortunate. Because when an experiment agrees with the theory, what you learn is very limited. It's when the experiment confronts with the theory, you learn something new. Well, let me summarize measuring the size of the electron. In 1967, we measured the size of the electron to be less than 10 to the minus 14. After many decades, we reduced, 3 decades, we reduced by 3 orders of magnitude. But it's very curious why you cannot find the size of the electron. So my 4th lesson is on a large international collaboration has become a trend in many areas of fundamental research. They involve many countries of diverse social and economic origins and often last for decades and spend 10 to the 8 to 10 to the 9 dollars. To have a successful international collaboration, you need to, most important, choose an important topic. So people would like to solve this problem. Give recognition to young scientists and respect the diversity of all your collaborators. And in some of our collaborations, some of our experiments, and we have people from India, from Pakistan, from China, from Taiwan, and many people with diverse backgrounds. And therefore, we do not discuss this, at least in our collaboration. To me, the most important thing is do not compromise on instrumentation. Build the best detector possible. If you don't, sooner or later you will regret it. And the fifth story, which I described this morning already, which I will go over very quickly, is the AMS experiment on the International Space Station. To have this experiment approved, we take Professor Waterstone and myself quite a bit of effort, because at that time, people were more interested in building a space station and to train the astronauts, and exploration was not on their highest priority. Let me acknowledge the presence of Dr. Roberto Vettori, who is a distinguished astronaut who put us into the space station. I mentioned the motivation of this experiment can be easily understood by realizing there are two kinds of cosmic rays. Light rays and neutrinos can be measured with satellites, large ground-based experiment, and I mentioned this CTA, it's a good example, and underground detectors like HEPS. Charged cosmic rays, the Earth's atmosphere is equivalent to 10 meters of water. The properties of charged cosmic ray cannot be measured underground because it's already dissolved by the time we reach ground. AMS in space is the only long duration, order of 20 years, which directly measure the original property of charged cosmic rays. On the ground, only the energy of cosmic ray can be studied by summing up the showers. I mentioned there were many discoveries of charged cosmic rays. Victor Hess first discovered cosmic ray. In 1936, he received the Nobel Prize after people proved the cosmic ray really is not from reflection from Earth, but from outer space, from outside Earth. Positron was discovered by Carl Anderson. Pi was discovered by Cecil Powell. And many subatomic particles were discovered. The space station provides the power and communication capability to support a precision particle physics detector to study primordial cosmic ray for the next 10 to 20 years. So this is the detector I would mention. It's not small, just fit into the shuttle, and it's not light. It has a capability to measure trillion electron volts. It is a very precise multi-purpose spectrometer. Particles and nuclei are defined by their charge, energy, or momentum. So transition radiation detector identify electrons and positrons. The 9-layer of silicon tracker measure Z and P. Electromagnetic calorimeter measure energy of positron electrons. 2 time-of-flight measure Z and E. Magnet measure the sign of the charge. Ring image counter measure Z and E. Therefore, charge and energy are measured independently by many detectors. You need to remember, once in space, if something goes wrong, you cannot send a graduate student to go to fix it. And therefore, it is very important to have redundancy. It is a large international collaboration with many countries, many institutes, and many physicists. And as I mentioned, Roberto Battistone, now the president of the Italian Space Agency, was a deputy principal investigator and really made this experiment possible by making fundamental contributions. In Italy, we have a very large national collaboration, many scientists, many universities and institutes, and we have 16 years of collaboration with INFN and Italian Space Agency. The coordinator was formerly Roberto Battistone, now is Professor Bruno Bertucci of Perugia. First, magnet. Before us, nobody has managed to put a large magnet in space, and the reason is very simple. A magnet in space will interact with the Earth's atmosphere, and soon your space shuttle or space station will lose control, because one end will always point to the north. Finally, we figured out a way to solve this problem, but to make sure we understood it, we actually built a magnet. The magnet was designed, provided by the United States, but manufactured in China, mainly because the best permanent magnet material come from Inner Mongolia, which is part of China. 7 magnets were made to understand the field calculation, field leakage, and dipole moment. 3 full-size magnets, 1 for space qualification, acceleration, and vibration, and second, destructive test. So we build a magnet. The magnet is made out of 4,000 pieces of permanent magnet material, and they're glued together. And you ask yourself, after some years, what happens if the glue doesn't work? And the shear force between the small pieces is 4 tons. And so if one go out, it will not be very good. And so we decided to build a magnet, try to destroy it, to see our supporting structure is strong enough to hold the magnet when the glue is no longer effective. Turn out we cannot destroy it because the supporting structure is very strong. The third is the flight magnet. Time of flight counter measures the velocity of charged particles, and there are always 2 banks with 2 phototubes each because of for redundancy. And this is the group of people from Bologna who built this system. Transition radiation detector is mostly done in Aachen with the strong participation from Rome and from MIT. They use the fact when a charged particle goes through the boundary of radiator, it emits transition radiation. And if you use a proportional tube, you can collect the transition radiation. And so these are the tubes we used. And took our collaborators from Aachen 10 years to build this detector. Silicon tracker is the major responsibility of Italy with support from many other countries. We provide a coordinate resolution of 10 micron, follow the heritage developed by Roberto in L3 experiment. And during the construction, Roberto showed to Senator Bill Nielsen, who is the chairman of United States Senate Committee on Science and Space. And this is Johann Dietrich Warner. A silicon detector have 9 planes, provide a coordinate of 10 microns. The coordinate resolution has no meaning unless you know where the detector is. And therefore, the inner tracker plane is aligned with the lasers, the 20 lasers. The outer one aligned by cosmic ray every 2 minutes. This is Professor Bruno Bertucci together with Roberto Battistone and Giovanni Ambrosi. They are the key people who made this possible. The ring image Cherenkov counter measures nuclear charge by the intensity of the Cherenkov cone and the velocity to an accuracy 1 part in 1,000 by the angle. And Giuliano Laurenti from Bologna made leading contribution in this effort. And these are the different Cherenkov rings for different elements on the periodic table at different momentum. So this is what the Cherenkov counter look like in the Spanish and the French group who construct this detector. The electromagnetic detector follows a technology invented by Franco Chiavelli. It's 50,000 fibers, 1 millimeter in diameter, distributed uniformly inside 600 kilograms of lead. It provides a precision three-dimensional 17 radiation length measurement of direction energy of positron electron to TeV. In 4 years on the space station, we have collected more than 65 billion cosmic rays, which is much more than all the cosmic rays collected in the last century, analyzed primordial cosmic rays. So let me give you some example of physics research. One of the research is search for the origin of dark matter, and I'm very impressed this morning there's a very active discussion on origin of dark matter, and I hope all the explanations are correct. Since 90% of the matter in the universe is not observable, that's why it's called dark matter. A galaxy, as seen by telescope, is something we are familiar with. But if you could see the dark matter, one model would predict it is like this. How to search for the origin of dark matter? Collision of dark matter, neutrino, will produce positrons and antiprotons. To identify dark matter signal, we need to measure positron, electron, antiproton signal accurately. So if you plot the positron normalized to positron, electron, you have collision of ordinary cosmic ray, which must decrease with energy, and then the excess depends on the mass of the neutrino. And this is true for positron, electron, and also true for antiprotons. So this is our first measurement. The first measurement, for a mysterious reason, fits rather well with dark matter model, one of the dark matter model. Whatever it is not from collision of ordinary cosmic rays. So this got the newspaper people very excited in New York Times, in Wall Street Journal, in the German newspaper, and also in the Italian newspaper. Many explanations. Last year, we have a new result based on 11 million electron positrons. With 11 million events, you can study this curve more carefully. You first look at the energy at which it begins to deviate from collision of ordinary cosmic ray. You must find this place where it goes up. Second, how does it go up? The rate of increase with the energy that matches with this. Are there any structures? Most important is you must find the maximum if it is this curve. And then you have to look how quickly it drops. If it's neutrino, it must drop quickly, mainly because of conservation of mass. So this is a major positron fraction of positron electron energy compared with the collision of cosmic rays, a low energy, the theory and the measurement agrees with each other. But suddenly, approach 10 GeV, it flies away. Flies away means you have a new phenomenon. The ray increase with the energy is rather smooth and there's no sharp structure. I mentioned already this morning, with so many million events, you can measure the slope. You see the slope goes up, flat, and then goes down, crossing zero at this energy. Slope crossing zero means you have reached the maximum. You no longer increase. So this appears in many articles in CNN, in Fox News, and some articles even reproduce our results. Now the key question is how fast it drops. So this is our measurement up to now. If it is from a pulsar, it will drop slowly. If it is from dark matter, it will drop very quickly because of conservation of energy. Our measure turning over energy favors dark matter, but of course doesn't prove it is dark matter. Let me make a comment, because this morning there were discussion whether this settles everything. If you measure antiproton when it have excess, then you cannot be from pulsars, because a photon in a strong magnetic field does not produce proton-antiproton pairs because the mass of antiproton. It's a point many people miss. This is the measurement of the electron and positron before AMS, and this is the electron coordinate, this is the positron coordinate. With this measurement from different experiments, you can have many theories, and in fact any theory you want. This is our measurement of the electron flux up to about TeV, and this is amplified signal. You can see how the signal changed up to this is to an accuracy for 1%. This is the measurement of positrons to 500 GeV, and this is you look more carefully in the first 200 GeV. The flux increases, flatten out, increases again. So this is the comparison of electron and positron flux. Looking at this graph, you see the electron flux and positron flux are different in their magnitude and energy dependence. Both spectra cannot be described by a single power law, and if you measure the spectrum phi as constant times e to the gamma, and then gamma equal to -3 is what people has assumed for many years, clearly do not explain our measurement. The spectral index changes with the energy. And most important, the positron and electron are different. We also published a paper last year on the sum of electron plus positron. This has been measured many times before because you do not need a magnetic field. And so these are the measurements, and this is the Fermi measurement, this is the other measurement. And because of the structure, it has received widespread attention from the newspapers. And this is our measurement. Our measurement shows there's no structure and also does not agree with anyone. Very interesting thing is the flux is consistent with the single power law, where the individual flux of the electron and positron are not, and the sum is consistent with single power law. We also measure the antiproton to proton ratio, and this is our measurement. A low energy agreed with the previous measurement, and then we go to much higher energy. As I mentioned, this measurement cannot be explained from theoretical prediction based on pre-AMS knowledge of cosmic ray collisions, and also cannot be explained by pulsars, because pulsar does not produce antiprotons. So the deviation from theoretical prediction for collision of cosmic ray show existence of a new phenomena. Whatever is the phenomena, it is not this, or pulsars. So I have mentioned the property of signal. We clearly need more measurement, but now we need to understand the background. Collision of ordinary cosmic ray will produce positrons, antiprotons. To understand this, we need to measure the cosmic ray flux of proton, helium, carbon, and so forth, and study the cosmic ray propagation from lithium, boron over carbon. This is our accurate measurement of cosmic ray production to 1%. This is the creation of the periodic table measured in space, and if you normalize them together, you will see your measurement can separate boron over carbon to the level of 1 part in 10 to the 3. This is our measured proton flux. This flux is very different from previous measurements and cannot be fit into a single power law. It mysteriously fit into 2 power law with gamma and gamma plus delta gamma. Because you have 300 million events, you can measure the spectral index as function of rigidity, and you see the spectral index is not a constant of minus 2.7, as people have used for decades, but it actually has a structure. Similarly, this is our measured helium flux. The spectral index of helium is different from proton in magnitude, but it's very similar in energy dependence, and it's not minus 2.7. This is a measurement of lithium. The lithium spectra goes down compared to previous measurement and suddenly changes behavior. So this is the summary. Proton flux, it is not a single power law as people expected, rather it changes structure. Similarly for helium, similarly for lithium. Slope changes at about the same rigidity for proton, helium, and lithium. So this new observation contradicts with the current understanding of cosmic rays. So the latest AMS measurement of proton or positron fraction, antiproton-proton ratio, and behavior of flux of the electron, positron, proton, helium, and other nuclei, providing new, precise, and unexpected information. None of our measurement fits with any theory. The accuracy and the characteristic of the data simultaneously for many different types of cosmic rays, but soon would determine the true nature of new phenomena we observe. So we will be in the space station for the lifetime of the space station. We will continue to do an accurate measurement to study dark matter, to search for existence of antimatter, or search for new phenomena. Let me give you another example, and that is search for the existence of antimatter in the universe. The Big Bang origin of the universe required matter and antimatter to be equally abundant at the very hot beginning. AMS on the space station will look for the existence of antimatter to order of 1,000 megaparsec. We know in the universe, in space, we have nuclear. The question is there anywhere in the universe there are anti-helium or anti-carbon? How do you detect antimatter? Cosmic antimatter cannot be detected on Earth because matter and antimatter will annihilate each other in the atmosphere. Matter and antimatter has opposite electric charge, so you need a magnetic detector to measure the charge of antimatter. Helium going this way, anti-helium will go the opposite way. This look for antimatter is a very interesting topic, in particle physics. Since 1967, when Andrei Sakharov produced baryogenesis, namely a theory of absence of antimatter. This theory requires breakdown of CP violation, namely the breakdown is 1,000 times stronger than the current measurement, and proton decays. Proton decay has been looked first by underground experiment in Japan, and this is full of photomultiplier, and this is a boat with 3 persons filling the phototubes. Proton decay has not been found. Despite 40 years of effort, new symmetry has not been found. So no explanation, no experimental explanation found for the absence of antimatter. So no experimental reason why antimatter should not exist. What we want to do is search for the existence of antimatter to order of 1,000 megaparsec for the next 20 years. So cosmos is the ultimate laboratory. Cosmic ray can be observed at energies higher than any accelerator. But the most exciting objective is to probe the unknown, to search for phenomena which exist in nature we have not yet imagined nor had the tool to discover. So let me share with you some of the discoveries in modern physics. When I first came to CERN, the proton synchrotron was the highest energy accelerator. The original purpose, in the experts' opinion, build this accelerator, you can study pion nuclear interaction to understand nuclear force. What was discovered was neutral current leading to the discovery of Z and W. In the United States, build a similar accelerator, also try to understand pion nuclear interaction. What was discovered, electron and muon have their own neutrino, CP violation, and the J particle. In Fermi Laboratory, the original purpose to study neutrino physics, what was discovered was the 5th quark and 6th quark. SLAC as sphere, original purpose was to do electron-proton scattering to understand electrodynamics. What was discovered was partons, 4th quark, and 3rd type of electron. In Hamburg, the original purpose is to look for the 6th quark. What was discovered was gluons. Super K is to look for proton decay, and what was discovered, neutrino has a mass. Hubble telescope, its original purpose is galactic survey. What was discovered was the flat curvature of the universe, existence of dark energy. And so you build a new instrument, you ask the best expert to predict what they will do, and when you do it correctly, most of the time, there's nothing to do with the original purpose. And so I have mentioned how important it is to look for dark matter and antimatter. But exploring a new territory with a precision instrument is the key to discovery. What ultimately we will see, nobody will know. But up to now, whatever we observe, is not what people thought. So for experimentalists, most important thing is to be curious, enjoy what you're doing, and work hard to achieve it. Now let me comment on the cost of research. I received this little cartoon and said that we just decided launching money directly to space was cheaper. And they definitely is correct. So in this century, we enjoyed unprecedented advancement in technological development, such as in the field of communication, computer, transportation, healthcare, and so forth, which have had a dramatic effect on the quality of life. What is often forgotten is that the foundation of this achievement was laid down some time ago by scientists who were driven by intellectual curiosity, not by economic concerns. So here is a triangle relate fundamental research and application. 100 years ago, in 1900, is 1930, and now today. 100 years ago, we studied optics, thermodynamics, and mechanics. Now it's used in television and aircraft. In 1930s, we studied quantum mechanics and atomic physics, now used for IT and lasers. In the 40s, we studied nuclear physics, now used in nuclear reactors. And so one way is to go to smaller distance. Another way is to go to large distance. In 1930s, the fundamental study was sun and cosmic radiation. Now it's used for navigation and timekeeping. So the space station is to try to explore extreme large distances. The pyramid grow with new application, increases height, where fundamental research widen its base. The role of basic research implies they define itself in the outermost corner of the pyramid. Hence, it's sometimes viewed as being remote from daily life. Only after some time, when application develop and public become familiar with the new phenomena, does the value of basic research become understood. So let me give you two examples. One is frontier science at extremely small distances. It's at CERN. CERN's recognizable achievement, first invention of WWW, which we all enjoy, and the discovery Z, W, and Higgs. Now let me give you an example, important example on fundamental science at very large distances. And the Italian Space Agency has now made a fundamental development to build larger and larger rockets. And I think the largest one now have a payload 1.5 tons. And with this, the Space Agency do a cosmic sky Mediterranean constellation. There are 4 satellites. These are most advanced synthetic aperture satellites. And with this satellite, you can measure the movement of the Earth. And this is vertical measurement in millimeter per year, minus 22 millimeter to plus 17 millimeter. And this is somewhere in Russia. You can see the landslide. And here is the highway, and here's the top of the building. So you can now measure in millimeter per year how things move. Really, it's an incredible thing. And this is an example in Nepal. And this is the change in 2014 with 2015 in the height. And this is before earthquake and after earthquake. And this is the relative change of height. So you keep a watchful eye on what's going on. And third application for frontier science at extreme large distances is trip to Mars. Trip to Mars, go in and back, takes 3 years. Galactic cosmic radiation is 90 rand per year. Lethal dose, even though nobody has accurately measured it, is supposed to be 300 rand. Therefore, without radiation protection, there's no need to come back. Also, 90 rand per year, 3 years is just 300 rand. So there's no need for you to come back. So there is a very important discovery, observation. I'm really impressed with Roberto Battistone, who lead this international collaboration, when at the same time lead the Italian Space Agency. This is an intellectual hobby. With a stabilized superconducting magnet with 3 coils and total 4 of them. In this way, neutrons does not interact into the cool compartment, and you have a magnetic field in such a way, and there's no magnetic field in the center. So a charged particle will not interact, will be bent away. And this is the only way you can go to Mars and come back. So the prime motivation for basic research is curiosity, the innate passion to learn something new and obtain a deeper understanding of natural phenomena. Results from basic research, though difficult to predict in advance, has had a profound effect on the society. Thank you.
Marvelous. Inspiring and really very beautiful. If I have to tell you the truth, I convinced my son to come here. And he listened and followed and every second and admired you.
You are much better than me. I will never be able to convince my son to come.
Let's have questions and any question? We are all, I think.
You can ask any question you want, and I try to do the best to answer you. And if I don't know that answer, I will tell you so.
Francis? Yes. Let's see if there is anyone who... Yes?
Yes.
Come. We don't have the microphone going.
If you go back and start our light over, what will you do?
This is a very good question. I often ask this question myself, and also my 2 daughters and my son. None of them are physicists. Ask me this. I would say probably, for me, probably not doing particle physics. Because when I started, it was still possible for few people to start experiment. Imagine if I just got my PhD. Imagine I just got my PhD, join a group of 5,000 or 3,000. It's a little bit hard to have your contributions known. I think Professor Bertucci and Professor Badison has always very concerned, together with me, how in a collaboration, young people to be recognized. So I would not know whether I dare to enter into high energy physics today. In my time, but still possible. Even though you can see that there were a lot of difficulties, a lot of objections in every one of the experiments we're doing. But you're still able to do it. But now I doubt it. I'm qualified to enter into this field. I don't know. Roberto, you have an opinion? Come. Yes, yes, yes.
Yeah.
Of course, that the size of the experiment increased dramatically, induced this kind of consideration about searching a field where it's possible to contribute in smaller groups. On the other side, it's also true that the way science is proceeding nowadays is significantly different than in the past. The amount of networking is incredibly larger. The evolution of ideas is much, much faster. I mean, and the amount of knowledge which is available and the tools to understand and following them is really different than 50 years ago, 60 years ago. So I think the most important thing is to have opportunity to train your mind to logical thinking and to science. Then if you have the opportunity to do that, typically it takes the context where few people are around, but they can also change with time. Then you better use as much as possible the wealth of resources to do whatever is needed to develop science at that time. Today, to develop science, you often need fairly large infrastructure and fairly large investment. There is no doubt about it, especially in physics. We heard this morning examples of that. Neutrino physics, AMS, and CMB is a demonstration how large it has to be a collaboration to provide progress in this field today. But so the issue is how to form the new scientists, not what they do, how to form them. When they have the opportunity to shape up their mind, they should do whatever is needed for the science of the time.
Yes, please. Yes.
You mentioned that you did some experiment where you were measuring the radius of the electron, and nowadays we know that the radius of the electron is smaller than 10 to the minus 17 centimeters. Mm-hmm. In a future experiment regarding the same topic, the radius of the electron, what do you think? I mean, when you do an experiment like this, which has fundamental importance for physics, do you do the experiment with some anticipation? I mean, do you do the experiment with having an idea in your mind what's going to happen, or you just follow strictly the facts? And what do you believe about the particular thing about the radius of the electron? Or what do you believe about the other fundamental experiments you mentioned, like does the electron consist of other particles, or do the quarks consist of other particles? What's your belief? I mean, is it going to turn up that they do consist of other particles, or the electron consists of other particles, or they are not point particles at the end? What's your belief about this?
My belief has no meaning at all. The important thing is to measure it. If you start doing an experiment, have a preconceived idea, and starting in making a cut up in here, cut in there, select events this way, that way, and sooner or later, you're going to prejudice yourself and produce wrong results. I presented questions, I have no belief. It would be a bad idea, at least for me, to believe I will get this, I will get that. The important thing is, if you don't measure, you will never know. So I have no belief. Yes? Go ahead, go ahead.
Okay. Do you have ideas for the change of slope in the fluxes? I know it's a speculation, but there must be ideas before we can find it.
No. The change of slope is correct. It's a measurement. Okay, there's no doubt about that.
What is causing it?
Huh?
Ideas for what is causing.
This I do not know. The data is only less than 1 year old, so we do not know. You must remember, cosmic ray in space before us was done by balloons and small satellites, and they have huge errors. And the theory was made to explain that. Now you have error very, very small. This is a new game. Yes?
First, thank you, Professor Ting. That's one of the most concise and excellent public lectures that I have ever heard. And so I have two questions. So the first one is that, so as an undergraduate student, I'm now just first involved in research. And I fully agree that curiosity is the fundamental engine for the research. But the work is tremendously, there's tremendous work to do. So to make it brief, what stands you, what stands your belief, what stands your curiosity in doing the research leisurely? I mean, this is just like 20 countries collaboration and spanning many, many years. What stands your belief?
Different people have different reasons. I can only answer for myself. For myself, I'm very curious what the result will get. Nothing else.
So the second question is that I read some of your biography a long time ago, and so you were actually studying engineering as an undergraduate at first. So what drove you into physics specifically?
First of all, I do not. In Chinese language, there are quite a few publications of me, but I think they have no experimental proof. So I'm distant from all these things. But it's certainly correct. In my first semester at University of Michigan, I studied mechanical engineering. I studied mechanical engineering mainly because I have no idea at that age, I really didn't know what I want to do. After one semester, my advisor had a conversation with me. He said, I could not, at that time there was no computer. You have to look at an object from the top, from the end, from the side. And I couldn't draw a line straight. So my advisor said, you are no engineer. And so you better go to physics. That's how I start studying physics. Yes?
Yes. I recall that many, many years ago when I was students, you start to talk about this experiment. And you mentioned this experiment is try to see the antimatter. However, you added, today you say, probably we will see something else. And exactly as why I can see, now you see something related to dark matter or something else you have to know. Not only just antimatter as initiated. But what I want to say more is look, this experiment could tell something, this in the space, AMS, could tell something for the ground, on a ground experiment, like in the CERN, or underground experiment. Means something you see in space, okay, which indicate or infer something should also be observed on the surface, on the ground, laboratory and underground. This what I got from you.
I do not know how to answer this. I think my main job is to make sure the experiment is correct. Because you need to remember, once you are in space, it go over your head every 93 minutes around the Earth, and you cannot look at it, and so you're always suspicious something could go wrong. And so I spend basically most of my time in the control room, look at the data, watch what could go wrong. If instruments sometimes misbehave, but once you know, you can correct it. But if some instrument is wrong and you do not know, you're going to make a mistake. So I basically spend all my time watch what's going on. So what you said may be right, may be so, but I've not thought about it.
Or probably vice versa. If something see in the space or underground, and you get indication what you're going to see in the space.
I better not comment on this, because I didn't think about these things. So there's a...
I have a naive outsider question about this dark matter detection. You mentioned that dark matter particle decay to electron and positron and so on. Is this model dependent? I mean, what if dark matter only gravitationally interact with our standard model particle? I mean,
I mentioned we measured positron, antiprotons, and these positrons and antiprotons is much more than the standard model cosmic ray can provide. Many people say, or positron ratio can be explained by pulsars, but the antiproton rate cannot be explained by pulsars, because the light ray in a strong pulsar magnetic field produces electron positron. It does not produce antiproton proton because the mass is so heavy. And so we have seen something new, or I can say we have not proved we have found dark matter, but all the measurement up to now shows no contradiction from the dark matter model. It will take us, I think, a few more years to see how quickly the positron fraction drops. A sharp drop from conservation momentum cannot be easily explained by any model except dark matter model.
Okay, thank you.
Very thought-provoking, and I think we all thank Professor Ting for his beautiful presentation. We have been enriched by his vision. My curiosity is, you went as a child to United States, if I understand correctly, and what was your going back to China, and how you see the development of China today, United States, and the progress which is going on the planet? What is your, how much you have been helped, even in your work, about the Confucius tradition, about the Chinese background, and how much you think you are just citizen of the world?
Not being a theoretical physicist, I don't know how to answer this question. And let me make two or three comments. My first comment is, after I was born in the United States at the University of Michigan, my parents took me to China. I was 3 months old, so I have no opinion about that. I do not feel I'm qualified to compare philosophy and social system between different countries. But I will submit you an observation. The philosophy of Confucius, 600 BC, and used in China for a long time, mostly deal with human relations. They never touch mind and nature. I think that's probably a correct observation. Confucius philosophy probably deal with human relation.
And this was the great merit of Matteo to bring the Galileo telescope to China, and we all celebrate this in the Galileo Xuquanchi meeting. And on that note, I would like to thank again for this splendid talk.